Assalamu alaikum. Welcome to this course titled Network Performance and Evaluation. I'm Junaid Qadir, the instructor for this course. So before we start formally with this course, let me introduce myself. I'm currently working at the School of Electrical Engineering and Computer Science, SEECS, at the National University of Sciences and Technology, also known as NUST. I'm currently leading a research group titled Cognet, where we're working on cognitive radio networks, which are a particular instance of or an evolved form of wireless networking technology. Before that, I've also worked in the industry, where I have worked for some of the largest data centers in Pakistan. I've worked for PTCL's Pakistan Internet Exchange, and I've also worked in NTC's data networking department, where I have practically seen and evaluated the performance of networks. Thereafter, during my PhD studies, I've also used the theoretical tools which I often used for evaluating the performance of networks. As we'd be seeing in this course, network performance evaluation is fundamental to any network operation. It is used during the research phase, during the phase in which we are thinking of what networking equipment to use, what algorithm performs well. So when we're comparing two different design options, so we're using network performance evaluation then. So let me formally start this lecture then by introducing the things I'll be covering in this lecture. So the first thing I'm going to talk about today is what networking performance evaluation is. So this would be a brief intro before I actually get down into the meat of this course. I'll be discussing both the contents of this course and also the associated resources that you would have to refer to for maximally benefiting from this course. So let us start with the first point, which is what exactly is network performance evaluation. So the first thing that we must note then is the pervasiveness of computer and communication networks in modern society. As you would appreciate, most of the businesses, the education industry, the media industry, the commercial industry, all of them are somehow reliant on the proper operation of networks. So we take this as a given because this is common knowledge that we in fact are so much reliant on computer networks that I would not be surprised that many of you would actually be even viewing this lecture on the internet. So having underscored the importance of computer networks, we need to understand how can we quantify the performance of computer networks. And we would need this theory of network performance and evaluation, which we will call NPE for convenience. So we would need a formal theory with which we can analyze computer networks both in the design phase and in the operation phase. And another thing that I'd like to talk about is when we talk of performance, it is a subjective term. So performance can mean different things to different people. So for someone, it may mean that the system should be cheap. For other people, it may mean that the system may actually be running a higher processor, for example, or the algorithm may actually be less complex. So we need to define what performance means, and then we would be seeing that actually based on the criteria we are looking at, the performance would be heavily dependent on what criteria we define. So this is one of the most important thing. Whenever we say that a system performs well, we need to provide context that in which particular scenario this system is going to perform well. So let us look at some common design analysis and evaluation questions that we would consider when doing network performance evaluation. So the first thing that we can talk about is design questions. That when we are designing computer networks, or we are conceptualizing what a computer network should actually be composed of, its software and hardware components, we can actually use the analytical tools offered by the theory of network performance evaluation to decide on the best design choice. As an example, if we assume a given packet arrival pattern and we then know what we are trying to optimize for, we can always solve the question that what should be, for example, be the amount of buffer space that your router must have. So this is an example of a design question. You have some performance in your mind and then you design the resources of your computer accordingly. Another kind of NPE question would be analysis and evaluation question, which would be relevant during the operations phase of networks. When it is operating, we need to see how well something is working. We need to quantify, whatever performance metric we think is best for capturing performance. We need to quantify in those metrics the performance of the network. So we've divided NPE, the broad field of network performance evaluation, into two kind of subfields. One would be the design sub-questions of NPE, and the other field would be catering to analysis and evaluation. So what are the goals of NPE? So we would be seeing that I've already mentioned two broad divisions of NPE. So we can actually be using NPE to compare two design alternatives. So whenever we are comparing two entities, these entities may be the same system with, for example, in a before and after scenario, that you have done some enhancement, you've done some modification or optimization, and you want to observe how much has the optimization improved the performance of your machine. We can also think of NPE goal as system dimensioning, which would mean again that with a particular performance metric in mind, you design your system accordingly. So we all know that we can buy different kinds of services from service providers. So we can ask, for example, that we need to have 99.999% reliability, but computer systems fail all the time. So how does a service provider go about ensuring this? So this again is a question of designing according to a particular goal. So this would then be a question of system dimensioning. Also, another important point is establishing models of relationships. How does some dependent variable depend on an independent variable? So let me clarify what I mean by this dependent versus independent variable. Usually we call a variable as an independent variable when we think of that as the causal agent, as something producing a change. And we call an independent a dependent variable which is affected by the change in the independent variable. So these two variables can be related in a correlational mode. So that would mean that one thing is not causing the other thing, but they actually vary in a similar manner. So for example, if one variable is increased, it affects the other variable in the same way that it is also increased, and vice versa. But we must be very sure that we do not construe this as causation. And we would be covering this much when we talk of statistics. It is a common maxim that correlation is not causation. And it's a common pitfall. So we'll be seeing how do we actually go about getting out of this situation where we construe a correlational relationship as a causal relationship. Lastly, we can also think of NPE in descriptive terms, that given certain parameters, we would quantify the performance of our system, which may be hardware, it may be software, in some particular metrics. So now, having described very briefly what NPE is, let me get down to what this course is about. So the first thing I want to mention about this course is the course outline. So this course, as you might know, is composed of 45 lectures, and this is the first lecture. And in the first lecture, I'm just actually introducing the entire course. What is NPE? What would be the contents of this course? What is the book you must follow? What are the associated resources? What are my expectations? What is the pedagogical design that I am following for this course? Because NPE is a subject which is a little complex. It depends a lot on logic, philosophy, mathematics, applied probability, and in many cases it is taught in a way which is inaccessible to students. Whereas I'd like to present this course in a friendly manner in which I describe not exactly the specifics of various techniques that are easily, accessible through software systems, but I'd be emphasizing on the broad important concepts, the fundamental concepts, so that if we understand those concepts, then it's just a matter of applying those concepts and looking for particular tools that would help you in doing your job. So after this first lecture, we'd be getting down into the modules of this course, and in all we have 3 modules for this course. The first module is titled The Science and Art of Network Performance Evaluation. So network performance evaluation is not purely science. It cannot be done in a mechanical way that you just describe a system and some computer, for example, or an algorithm would give you what this system's performance is. It does not work that way. It is also, it involves lots of judgment. It involves lots of insight which one can only acquire after years of experience working with systems. So we have to balance both science and art when doing NPE. And the first part of this course is actually just going to inform you of these fundamental concepts and put in front of you the need of doing both of these things in balance. So in the first module, which is going to be 12 lectures, so it will start from lecture 2 and it will go on till lecture 13. So again, this module is divided further into subparts, and in fact we have 3 modules, and all of these modules have 3 subparts, and all of these 3 subparts actually encapsulate everything that we have to know about this module. So in this lecture I'm just talking about these subparts, and the specifics of these subparts we'll actually get to in due time when we get to those lectures. So we begin with what are the subparts of the first module titled Part A. So in Part A there are 3 subparts. The first thing is the science of NPE, and this would be the next lecture, in which I describe that we have to perform NPE in a scientific way, in which we use evidence and mathematical logic to draw conclusions. So it should not be opinion based, or we should not believe in myths. So we have to be dispassionate and objective about the entire process. So we would actually see in the lecture when we get down to studying the science of NPE that the science of NPE actually involves the dependence on empirical observations. So for example, it does not matter whoever is saying that some system performs well, but we have to see this empirically. And there are other things involved. I'd mention that when I get to the science of NPE, when I get to describe that. The second subpart of this Part A is about statistical background and statistics, the grammar of science. Because to do science, and as I've mentioned, the bedrock or the foundation of science is the dependence on empirical observations. And again, when we observe something, we can generalize some theory which explains whatever system we're considering. So we would be naive if we just generalize on the basis of 1 or 2 observations. We need an entire science which will help us decide what conclusions to draw from data and how strong those conclusions must be. And lastly, an important point of the science and art of NPE is the component of NPE which is judgment based. So we'd be seeing that science proceeds by proposing models of whatever you're considering. So any process, you model it and you use that model to explain how the system under consideration would perform. Another important part of NPE, which is again more of an art than it is of a science, is how do we present data. It's important that we do not use statistics and data to mislead people and to mislead ourselves. So in this part, we'd be seeing how do we present data in a form which informs and which helps people and all the relevant stakeholders take informed decisions. So the first part of science and art of NPE is the science of NPE, and I've chosen two quotes which I think encapsulate the spirit of science. The first quote is by the famous physicist Richard Feynman, who said that the fundamental principle of science, the definition almost, is this: the sole test of the validity of any idea is experiment. Okay, so let me clarify what this means. This actually means that all armchair speculation in which you actually just reason about things, you're not actually confirming with reality, or you're not actually performing experiments, that is all outside the scope of science. Everything in science has to be verified empirically. Empirically का यहाँ मानी ये है कि हम observe उसको करेंगे. जब हम उसको खुद observe करेंगे और वो corroborate करे, which means it confirms our theory, only then we say that our theory has passed the test of observation. And obviously we cannot just generalize from a single observation. We have to not only passively make some observations, पर जो हमारी theory होगी उसको actively falsify करने के लिए हम experiments करेंगे. So actually science works in a funny way in which you propose theories and that theory is not accepted until you try to falsify it. So you think of experiments which can falsify your theory, and if even after those experiments your theory has actually good correspondence with actual observations, you would say that this theory is a good model of reality. Another component of science is that in science, opinions of people do not matter. So even if Newton says something or Einstein says something, or you can take your pick of modern, big physicists or scientists, it does not matter what their opinion is. If their opinion is not backed up by evidence, we as the scientific community do not take it. So let me give you an interesting quote from Galileo, who is one of the foremost scientists. So whenever we talk of the scientific method, Galileo is credited with giving prominence to the current mode of the scientific method, which depends a lot on empirical observations. So Galileo said, in questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. So again, it confirms the things we've mentioned earlier, that science does not depend on opinion. It depends on evidence which is observed after controlled experimentation, and those observations are independently verifiable. So it is part of science that whenever you have a theory, you should publish all the experiments that you've performed which confirm your theory, and also all of the experiments which do not give a good which do not give good results for your theory, in which there is not much of a match between data and what your theory predicts. So in this matter, science progresses. The next thing is when we're doing science, we have to deal often with lots of data. And how do we reconcile all this data? We have to use what I call the grammar of science, or statistics. Statistics helps us make meaning from data. So to illustrate this, let me give you a common saying. It is often said that someone who has only one watch knows the time, but someone who has two watches is always confused. So what then is better? From a scientific point of view, it is better to be confused in this way. It is because this helps you in understanding that there is discrepancy, and it might be that the preciseness that which you are judging your measurements to be with is inexact. So it may be, in this example, the person who is only depending on one watch, if this watch drifts out of the actual time, that person would have a false sense of security. So which is what we do not like in science. We do not like false sense of security. A quote by John Tukey, the famous statistician and mathematician, who also, by the way, invented the word bit, which we often use, which is a contraction for binary digit. He said that it is better to be approximately right than be exactly wrong. So in this example, the person who is just depending on one watch is content in his mind, but he is being exactly wrong. He might be exactly wrong in some cases, and in those cases he would not have any clue that he is wrong. But someone who depends on two watches or multiple watches and confirms the variation between these sources, he would be approximately right. He would know the margin of error between the different readings, and he would know then that, the more readings that you have that are consistent would only increase the probability or the confidence that person has in those measurements. I'd like to also tell you another relevant quote. Ernest Rutherford, who was also a physicist, he actually said something about statistics and experimentation. He said that if your experiment requires statistics, then you need to perform a better experiment. I think that is bad advice, because having more data cannot harm you, and in fact it gives you more information, and you can know the margin of error in your measurements. It is for good reason that the body which manages the world clock, or the official standard world time, actually uses a lot of atomic clocks and averages them, so that you also have accuracy, because these atomic clocks are very accurate, but you also have preciseness, that you have an idea about if a certain clock drifts out of time, you have an idea because you have multiple sources. So statistics is very important because it provides us context about data. So it's not only numbers then, it is the insight that you gain from numbers. So I would stress that statistics is perhaps, along with the mathematical side of NPE, the queuing theory, and the analytical aspects of applied probability, this is perhaps the most important area of knowledge that we must understand if we are to perform NPE efficiently and accurately. Lastly, in the part of science and art of NPE, the last subpart is about the art of NPE, in which we are concerning ourselves with primarily two things. The first thing is, how do we model some phenomena. So this phenomena may be a process which you want to perform analysis of, and it is cost prohibitive to actually do experimentation on a system. So iski example ek ye hai ki whenever you're doing destructive testing, or you are doing something which is not desirable. So for example, if we want to know that at what level of performance would the customers be complaining, or the customer's complaint would increase above a certain threshold, you actually do not want to do this in a live network, because this disturbs the business of the company. But you can actually draw a model of your network, and then you can manipulate with that model. And I've already mentioned that the basis of all science is dealing with experiments. And when you cannot perform experiments, the next best thing is to actually play with a model. In fact, even when you can perform experiments on a system, for example, in scenarios where it is not either cost prohibitive or it's not detrimental to your business, still it might be useful to have a simple model which approximates that system. So when we get to this part of the course, we'll be seeing that you may have, for example, mathematical models. In mathematical models, you describe a system through some mathematical relationships. So we must understand that this mathematical relationship will not capture all the properties of a system, because any mathematical relationship is an abstraction. So it's important that whatever model we have then is, for our purpose of performance evaluation, it's a good approximation of the important points of the system. Another point which I would call as part of the art of NPE is how to effectively present data. So we are all the time consumers of statistical information, and in many cases this is presented to us in a visual form. So we're all aware of data being presented in tabular forms, in the form of charts, in the form of bar graphs. So in certain cases, some data is more amenable to representation by, let's say, a bar chart. In other cases, let's say when you have multiple variables, you might need to think of alternative ways of representing data. So in this part of the course, we'll be seeing what are standard good practices that we must know, and what are the common pitfalls that we must avoid. So this describes the part in which we talk of the science and art of NPE. The second module of this course is dealing with experimental NPE. So the first part has ramifications which apply to this module and the next module, जो हम बाद में देखेंगे. But still, we only described what is the experimental method. But in this module, we'll be describing the details of how to do experiments, how to do science that is based on experiments. So let's see the subparts of this module. So there are three subparts here. The first part is workload modeling. The second part is the design of experiments. And the third part is internet measurement. So let's start with the first part, which is how do we model workloads. So this again is related to what we've already mentioned about the art of NPE. We've already mentioned of models being approximations of reality. So let's say you want to measure a system. We have to describe the workload on that system. कि किस किस्म की request उस system पे आ रही हैं. And in fact, you would observe this as we go on in this course, and you would learn that NPE, Network Performance and Evaluation, is critically dependent on workload. So, अगर आप workload change करते हैं, the conclusions that you were drawing earlier may actually be null and void, because changing the workload may change the performance of your system. The system may perform well under a certain threshold, and it may not perform well above a certain threshold. So it's important that we accurately model the workload on our system, whatever system we're considering. So for this, again, we use the tools of modeling. जो हमने बात की थी, the art of modeling. How do we decide what kind of a model is better? So in fact, the third module of this course is only about modeling. उसमें there are two ways of doing modeling. One of it is analytical modeling, in which you represent a system which whatever we're considering for doing network performance evaluation, and represent it as mathematical relationships. So this is known as analytical modeling, and queuing theory is the prime tool in this area. The second aspect of modeling is those models which cannot be abstracted in a simple way, which has a ready and closed form solution. So if you have a system like that, and most real systems are like that. उनकी approximations आप नहीं कर सकते because if you abstract away some details, it may be unrepresentative of the system at hand. So it depends on the kind of NPE problem that you're looking at. If your problem is very complex, the chances are less that you would have an analytical solution available. In those cases, you have the option of doing computer simulation modeling, in which you model the phenomena that you want to study as a computer simulation, and then you run that simulation and see how it performs. And based on the results that you have, you can draw some conclusions. So one quote which I think again is representative of the spirit of workload modeling is that the essence of modeling, as opposed to just observing and recording, is one of abstraction. This means two things: generalization and simplification. तो हम देखेंगे कि जैसे फॉर एग्जांपल कुछ मॉडलिंग टेक्निक्स ऐसी हैं जो कि बहुत जनरल हैं. So those apply to many broad systems. For example, जब हम queuing theory की बात करेंगे, many practical systems ranging from the waiting line at a grocery store, or the waiting line at a bank, or the packets arriving at a router, they can be approximated as a queue. And then we can use the theory of queuing theory to actually approximate and analyze the network in a way which gives us ready-made solutions. The next important part of experimental NPE is the design of experiments, and this is a part of NPE that is often overlooked in NPE courses, because often NPE courses are overly emphasizing on the analytical or mathematical aspects of NPE, whereas statistics and experimental design issues are equally important. So we've already mentioned that science proceeds in a way in which you propose theories and then you compare the predictions of your theory against actual data. And if those are in accordance with each other, you would say that this theory is a good model of reality, or your confidence in this model increases, and then you think of other ways in which you should be performing experiments, because whenever you propose a theory, you must also accumulate all counter evidences कि ठीक है ये काम करती है theory in these particular scenarios, लेकिन what about all the other scenarios? You cannot just cherry pick a few scenarios in which your theory works and just disregard the other scenarios. So an important area in which this thing is applied and from which we can easily understand the design of experiments is medical trials of the effectiveness of different drugs. So for example, if someone gives you a magic pill and tells you that this is the perfect cure for whatever sickness, how do we actually examine this claim in a scientific way? अगर इस दवाई से let's say एक दो लोगों को आराम आ जाए, can we conclude that this medicine is effective? Not if we talk in the terms of science. For science, this is not a strong enough evidence for drawing this conclusion that this medicine is actually effective. So actually जब हम design of experiments की बात करेंगे तो इसके अंदर काफ़ी जो है nuances हैं. आप देखेंगे कि आप controlled experiments करते हैं. So you decide a few subjects to which you would be giving this medicine and some other subjects to which you would not be giving this medicine, and then you would be seeing how do they compare. क्या ऐसा तो नहीं है कि जिसको दवाई मिले वो भी ठीक हो जाता है और जिसको दवाई ना मिले वो भी ठीक हो जाता है. So in that case we cannot really conclude that the effectiveness is in this medicine. तो design of experiments एक काफ़ी important field है, और when we get to this part we'd be covering this in much detail. Lastly, in experimental NPE we'd be talking of measurement, and again measurement is a critical part of the scientific method, because measurement is the data upon which you base your models and it is actually the data upon which you base your conclusions. So it's important that we have measurements. जब हम workload modeling की बात भी करते हैं, तो your workload model cannot be divorced from the actual data measured. Because if you are making certain assumptions which are not backed up by actual data, then your NPE study is in risk of being ineffective. Or even worse, the results that you may have may actually be false, and you might be in the false security that your system is performing well क्योंकि आपने कुछ assumptions के हिसाब से analysis की, but unfortunately those assumptions are not correct. So measurement is very important, and we'd be covering how to actually do measurement based studies. So this would complete or wrap up our discussion on module 2. And lastly, we'd be finishing this course by having the third part of this course, in which we talk of simulation modeling based NPE. We've already mentioned the need of simulation and modeling. I'd be reiterating. We've mentioned that in many cases it is not the option of experimenting on real system is not available, or even if it is available, it may actually be disruptive to the performance of the network. So in that case, we can actually get better and more efficient NPE results by just doing these analysis on a model of the actual system that we're considering. And when your actual systems are very complex, then often you cannot have mathematical relationships describing the system. So in those cases we'll be using computer simulations. So इस module में essentially 3 part हैं. The first part is about the mathematical preliminaries that we have to know to understand analytical modeling, queuing theory, computer simulation modeling. This would include a study on randomness, about stochastic processes, about commonly used distributions. So the first part, the part in which we talk of stochastic background, so in this part we'd be covering important points regarding how we can use the concepts of probability, randomness and chance in understanding the performance of whatever system we're considering. Because and one point that we must remember is that all experimental observations are liable to being affected by artifacts, or in other words, all observations, all measurements have some error in them. So this error is not the common error that we think of. ये blunder की form में ये error नहीं होता. Every time you do an experiment, there is bound to be some variation in the results that you have. So to understand this, we cannot represent the performance of a network by a single number, or even if we do, in certain cases we have to represent the performance of a system but through some central tendency number like an average or a mode or a median. But still this single number does not capture the entirety of the results. So in those cases we need to know, for example, the probability distribution with which the results are coming, और उसको भी इस actual empirical जो हम observe कर रहे हैं data को, उसको भी हम model कर सकते हैं. और ये इन model को हम common distributions कहते हैं कि आमतौर पे we can abstract that okay, your actual data is representing a normal distribution. ये आमतौर पे तब होता है where data is centered around a central value. Or we may think of a distribution of some random variable being represented by a Poisson distribution. So एक तो चीज़ हम पढ़ेंगे common distributions इस part में. Secondly, probability और stochastic का review भी हम करेंगे in this part, so that we are able to understand the subparts that follow. और इसके फ़ौरन बाद हम पढ़ेंगे analytical modeling. So what is analytical modeling? Analytical modeling is the representation of a system through some analytical मैथमेटिकल रिलेशंस। तो आमतौर में इस पे जो सबसे इसकी जो प्राइम थ्योरी है वो क्यूइंग थ्योरी है, which has been extensively used for modeling telephone networks and also all kinds of networks, computer and communication networks. As an example, we can think of some packets are arriving at a router and they are queuing up for service from the router. Router takes up one packet and performs the appropriate switching operation. अब इस चीज को हम abstract कर सकते हैं by the notion of a queue. So this is the abstract notion of a queue, और इसी को हम इस्तेमाल करके बहुत सारे और results बहुत सारी और जगह इसको apply कर सकते हैं. As I've already mentioned, you can model the queue that we form in a grocery store by this. जहाँ भी you have a server that is shared by multiple clients, you can use the queuing theory. और queuing theory अगर एक accurate model है आपके network का या जो भी system आप consider कर रहे हैं, तो actually इससे बहुत जल्दी आप results gain कर सकते हैं, because इनके analytical results available हैं, and whenever analytical modeling is applicable, it is actually desirable to use this. क्योंकि simulation modeling में you actually first of all need to make elaborate model of the system. उसमें काफ़ी programming involved होती है, और typically उसमें हमें काफ़ी ज़्यादा time लगता है, because even after making a computational model, you have to ensure that you run simulation so many times कि जो results आप उससे infer कर रहे हैं या जिस result के ऊपर आप conclusions draw कर रहे हैं, that is actually representative of a system. So जब हम इस part में जाएंगे तो हम देखेंगे कि systems का एक transient behavior होता है और एक average steady case behavior होता है. तो उस case में simulations may take a very long time, but when we are considering analytical modeling, this actually gives us very quick and prompt results, subject to the condition that this thing is actually relevant. Agar if something cannot be modeled by this, then if we model it through a queue, aapka result obviously will not be valid. So the last thing that we'll be doing in part C is simulation modeling. और simulation modeling को motivate पहले मैंने ऐसे किया था by mentioning that simulation modeling is relevant when you have a system that is very complex, or if you have a system that is not going to take kindly to being disrupted from your modeling study. So if you have a system like that, you can always use simulation modeling. And in fact, if you have the time, you can build simulation models for practically any performance system. तो ये सबसे ज़्यादा general solution है, लेकिन we only apply it when an analytical solution is either not relevant or the assumptions are actually too much. We cannot approximate the system, or we cannot reasonably approximate a system through analytical model. तब फिर हम simulation model को इस्तेमाल करते हैं. और सिमुलेशन मॉडल का बेनिफिट ये है कि ये सबसे ज़्यादा जनरल टेक्निक है. इससे आप किसी भी NPE सिस्टम को मॉडल कर सकते हैं और उसको एनालाइज कर सकते हैं. सो ऑल्सो इन दिस पार्ट वील बी सीइंग दैट ओके यू बिल्ड अ सिमुलेशन मॉडल एंड यू हैव सम रिजल्ट्स. सो व्हेन डू वी ड्रॉ द लाइन दैट वी हैव इनफ रिजल्ट्स एंड वी कैन ड्रॉ कंक्लूजन्स फ्रॉम दैट. तो अगेन उसमें स्टेटिस्टिक्स भी इन्वॉल्व होगा, और उसमें वही बात आ जाएगी कि डेटा से कॉन्टेक्स्ट या जजमेंट कैसे हमने एक्सट्रैक्ट करनी है. Okay, so this does it for a description of the course. Lastly, the 45th lecture would be the conclusion of this course. What ground we've covered in this course, what are the other things that we can cover, how can you actually follow up this study to actually do practical implementation of the ideas that we've learned in this course. So this would wrap up this course. Uske baad another thing which is actually very important for your knowledge is that what resources are available for this course. तो अब मैं इसके बारे में बात करता हूँ. Firstly, what textbook we are going to use. तो उसमें the thing is that, specifically for all the topics we are covering in this course, I think no book exists which covers all of these materials. But the choice that I've made is the classic book titled The Art of Computer System Performance Analysis by Raj Jain. Isme, I want to emphasize that this book is not centered on network performance. It is basically dealing with computer systems performance. So computer systems ki performance is more general. Network is a more narrow term. Lekin many of the techniques described in this book would be relevant to this course. So I've chosen this book as the prime reference for this course, or you may call it the course textbook. Also, I'd be authoring a guidebook in which I'd be listing down some important resources. In the modern world, I think it's very important that we realize that currently the information is available in such abundance that it would be obviously not optimal if we just focus ourselves on the book. So for different things, you have different resources available on the internet to help you understand that. So I've actually made an attempt to gather all of those links. Usko maine accumulate kiya, and I've also written down notes for each lecture. So you'd be able to find this as part of the course guidebook. इस कोर्स की वेबसाइट्स भी कुछ हैं जिसमें आप कोर्स रिलेटेड मटेरियल देख सकेंगे, दी पावर पॉइंट्स and all the related resources, the links, the demos, the interactive applications. So as is usual for all VU courses, you can actually use the VU LMS to access the course website, or a standalone website भी I have created in which I've listed down all the 45 lectures, and for all of those lectures I'd be giving you some notes and some links that you can do as an exercise. Har lecture ke baad you should go to this site and to the VU LMS to find out the relevant resources for that particular lecture. So with this we're coming to the end of this lecture. Aaj ke lecture ke liye it would be helpful if you can see chapter 1 of your textbook to get a general feel of what network performance evaluation is about. Obviously that chapter is not entirely covering the topics, because we've made a selection of topics which I believe is most relevant to the practitioners of network performance evaluation. So the important point is the practitioners of network performance evaluation. So network is critical here. चूँकि ये किताब कंप्यूटर सिस्टम से relevant है, तो you might see some topics which I've covered in my lecture which you will not be finding explicitly in that book. So for all those topics you are encouraged to see the course website and to explore all the links available on the resource page. So that wraps up the discussion on the course outline and generally concludes lecture 1. I'd see you next time inshallah when we discuss the scientific method. Thank you.